All right, so welcome to my lecture on the gamma distribution. Okay. And before we talk about the gamma distribution, I'm going to talk about the gamma function, which is actually something that you've seen before. So the gamma function is gamma of alpha is equal to this integral from 0 to infinity of z to the alpha minus 1 times e to the minus z dz. Now, one thing that I'd like to note is that just by composition, this gamma of alpha plus 1, instead of having an alpha, I'm going to replace alpha by alpha plus 1, and we're going to get that this is the integral from 0 to infinity of z to the alpha plus 1 minus 1 times e to the minus z dz. Okay, and here's one more fact. Gamma of 1 is this integral from 0 to infinity of z to the 1 minus 1 times e to the minus z dz. Okay, so this just becomes a gigantic 1, so I can pretend that this doesn't exist. Okay, and this is an improper integral, but I'm going to neglect that for now. It becomes minus e to the minus z, evaluated from 0 to infinity. When we plug in infinity, that limits to 0. Plus, the double negative makes it a plus, e to the 0, which is 1. Okay. Here's another fact that I'd like us to recall, and that's integration by parts. U times v prime equals u times v minus this integral of u prime times v. That's integration by parts. And I'm going to use that here on the gamma function. Okay. So here I'm going to let u equal z to the alpha minus 1, and u prime is going to be alpha minus 1 times z to the alpha minus 2. Okay. V prime, that's going to be equal to e to the minus z. So v is going to be minus e to the minus z. Okay. So now, once we use this integration by parts, we can write this gamma function as this integral from 0 to infinity z to the alpha minus 1 times e to the minus z dz. So by parts, this will be equal to z to the alpha minus 1. Then the negative comes from the e to the minus z minus this integral of alpha minus 1 times minus e to the minus z dz. Okay. Now to evaluate this part, when we plug in infinity, that's technically L'Hopital's rule, but I'm going to skip the L'Hopital's rule and tell you the result is going to be 0. Minus when z is 0, it's going to be another 0. Okay. Plus alpha minus 1 times this integral from 0 to infinity. And here this should be z to the alpha minus 2. Just forgot to write that. z to the alpha minus 2 times e to the minus z dz. So perhaps I should just rewrite that so that we can see it a lot more clearer. So that's going to be alpha minus 1, integral from 0 to infinity, z to the alpha minus 2 times e to the minus z dz. And we can recognize this as alpha minus 1. This piece right here, that is called gamma of alpha minus 1. So this is going to be alpha minus 1 times gamma of alpha minus 1. Hence, there's two important properties of the gamma function that I want to tell you about. So the gamma function has this property. One is that gamma of alpha is equal to alpha minus 1 times gamma of alpha minus 1. The second property is that gamma of 1 is 1. So here's going to be a quick example. Calculate gamma of 5. Gamma of 5, I'm going to use that second property, is going to be 5 minus 1 times gamma of 5 minus 1. I think that's going to be 4 times gamma of 4. So that's going to be 4 times, well, 4 minus 1 times gamma of 4 minus 1. So that's going to be 4 times 3 times gamma of 3. And then I can use the property one more time. It's going to be 4 times 3 times 2 times gamma of 1. Well, gamma of 1 is 1, so that's 4 times 3 times 2 times 1. I'm pretty sure that's 5 factorial. So the gamma function is a factorial. And that's just a neat little fact. Okay. Now, there's one more thing that I'd like to talk about, which is a gamma density. Or distribution. And the gamma density is going to be this 1 over f of x divided by 1 over gamma of alpha times this beta to the alpha times x to the alpha minus 1 times e to the minus x over beta. And that's if x is greater than 0, and also alpha and beta are also greater than 0. Okay. Now, here's a couple of facts that I'd like to prove, and I'd like to calculate e of x, a gamma random variable. Okay, and we're going to start by using the definition of e of x. Okay, so just remember e of x, that's going to be this integral from minus infinity to infinity of x times f of x. Now, we don't have to integrate from minus infinity because the gamma density only applies for x starting at 0 and going to infinity, and that's going to be x times 1 over gamma of alpha times this beta to the alpha times x to the alpha minus 1 and e to the minus x over beta dx. Now, let's simplify this. This is a constant. So I can take that outside of the integral. Okay. Then I'm going to put these two terms together. That's going to be x to the alpha, and this is going to be e to the minus x over beta. Then I'm going to do a substitution here. And it's going to be w is going to be x over beta. Okay. So 1 over gamma of alpha times beta to the alpha times this integral. And remember that this integral had limits in terms of x, so I'm going to rewrite them in terms of w. So when x is 0, w is 0. When x tends towards infinity, w tends towards infinity. Okay. And now I'm going to get e to the minus w. dw dx is going to be 1 over beta. So instead of having a dx here, beta times dw is what I'll have. So I'll have a beta times dw. And also remember that x is equal to beta times w. So I'll back substitute that in here. Okay. Now, these betas are constants, so I'll move them outside the limit of integration. So I'll have beta to the alpha plus 1. Okay. And I'll have gamma of alpha, beta to the alpha, times this integral from 0 to infinity, times w to the alpha minus 1 times e to the minus w. Now, if we look at this piece right here, we can actually recognize that. Okay. And let me just first make sure. Okay. So let me just do one thing right here, which is it's w to the alpha from the previous line. Okay. One thing that we can recognize this as, okay, we'll cancel that and we'll cancel that. And we'll have beta over gamma of alpha, is that this is a gamma function, but it's off, and it's off just slightly. So to make that a gamma function, that's gamma of alpha plus 1. And now I can use the property of the gamma function. That is, I'll use its alpha times gamma of alpha. And now I'll get that the expected value is beta times alpha, and that is e of x. Okay. Here's a few other facts. Is that the variance of x is going to be alpha times beta squared, and its moment generating function is going to be 1 over 1 minus beta t to the alpha power. Okay. So here's the other fact about the gamma function. When alpha is equal to 1, we get the exponential function. Exponential distribution. Okay, and I'm going to talk a little bit more about that. Okay. Here's another fact. When beta is 2 and alpha is equal to gamma over 2, you're going to get what's called a chi-squared distribution. Okay. But now back to the exponential. So if I wanted to talk about the exponential, okay, I'm going to have this scenario where the density f of x is going to be 1 over beta times e to the minus x over beta if x comma beta are greater than 0. This is the exponential density or distribution here. Okay, we also know e of x is equal to beta, and moment generating function is going to be 1 over 1 minus beta t, and other good stuff like that the variance of x is equal to beta squared. Okay, but here's a quick example. The length of telephone calls is believed to have exponential distribution. With beta equal to, not 2, but 5 minutes. I can ask you to calculate the probability the call or conversation lasts longer than 7 minutes. Now, if I want to calculate this, I should declare my random variable here, x. In this case, x is the length of the telephone call. In minutes. And I'm being asked to calculate probability x is bigger than 7. Okay. Now I can do the complement just because I prefer not to deal with the improper integral. So if I do that, I'll get this, and I'll get 1 minus the integral from 0 to 7 of 1 over 5 times e to the minus x over 5 dx. That's easy enough to anti-differentiate. When I anti-differentiate that, that'll be minus e to the minus x over 5. Okay? and is off by a negative sign, so that should be a plus. Evaluated at 0 and 7, and then I'll have 1 plus e to the minus 7/5 minus e to the 0, and my final answer is just e to the minus 7/5. Okay, and that's the probability that I am left with. Okay. Now, one more thing or remark is that we had to assume that the density was exponential. And if I look at the exponential function, it looks something like that. There's x, there's f of x. And what this says is that the histogram, which I haven't formally talked about yet, looks something like this. It says that the probability of a call lasting a long time is very low, and the probability of it lasting less than the average is pretty high. There's one other thing I'd like to talk about, which is this theorem 4.3.3. And it says this. Okay. If X has a Poisson process, with parameter lambda, and W denotes the time of the occurrence, the first occurrence, then W has an exponential distribution with parameter beta equal to 1 over lambda. And let's give an example, but let me give you more space. Okay. The breakdown, or let me say this, the electrical parts fail on average once every 12 years. So here I have a Poisson process because X is Poisson, and this is equal to the number of broken parts every 12 years. And what the theorem is saying says that if W equals the time until the next breakdown, then W has exponential distribution. Okay, and here lambda is going to be 1 breakdown per 12 years. So the theorem tells me that beta is equal to 12. Okay. So if we were asked to calculate the probability the part takes longer than 15 years to break, we can calculate that. We're asking the probability W is bigger than 15, and that's going to be 1 minus the probability W is less than 15, which we can integrate, and we'll do 1 minus 0 to 15 of 1 over beta, so 1 over 12 times e to the minus W over 12 dW. Finally, we're going to get 1 minus e to the minus W over 12 from 0 to 15. And this is going to be 1 minus, that should be a plus, e to the minus 15 over 12 minus e to the 0, that's going to cancel, and I'm going to get e to the minus 15 twelfths. And that is the final answer. Okay, so this was just a brief lecture on the exponential distribution, the gamma density, and the gamma function. I hope you enjoyed it. Thank you very much.